Welcome to our new unit, Chemistry 1 in Year 10 Science. In this unit, we're going to be recapping some of the chemistry that you've learned up until this point, and then we're going to start building on it with some new and exciting chemistry. So what is chemistry? Well, chemistry is the study of all the materials on Earth and in space. It studies the properties of materials. It looks at why materials act the way they do, how they act and interact together. And that it allows us to really understand the world and universe around us. And it has allowed advances with humans to understand the properties of materials, to be able to evolve and develop technology. It's a very important science, is chemistry. But at the base of all chemistry is the atom. And to understand chemistry, we need to understand about the atom and how an atom functions. Okay, so here we have a 3D representation of an atom. And our atom is made up of protons. They can be the little red dots in the nucleus there. Neutrons, the little white balls in the nucleus there. And then our electrons that are spinning around the outside. We say they're orbiting the nucleus. They're held there by some electrostatic charges. All right, let's learn a bit more about our atoms. Okay, so the study of atom we call the atomic theory. And all matter is made up of atoms. Solids, liquids and gases, everything is made up of atoms. Now, atoms are neutral, okay, they don't have a charge, but they are made up of charged particles, okay, so these are these subatomic particles that we've just been talking about, our protons. Now, protons have a positive charge, and we say they have a mass of 1. Neutrons, they have no charge, they're neutral, neutron, neutral, no charge, so positive, neutron, no charge. And then we've got our electrons. Now, electrons, they have a negative charge. And if we look at the size of them, okay, protons and neutrons have what we say is a mass of 1. But our electrons, they are very small compared to a proton, okay. Now, as I said, these atoms are held together by this electrostatic attraction. The neutrons and protons are held in the nucleus due to electrostatic attraction, and then the electrons are orbiting the nucleus due to that electrostatic attraction as well. Okay, now atoms of elements are written using the following notation. So we have what we call an atomic number. And this is the number of protons in an atom. So atomic number is the number of protons in the atom. Mass number is the number of protons and the number of neutrons. So basically, the number of subatomic particles in that nucleus. The number of neutrons, you can find this out by taking the mass. If you have the mass number, and you take away the atomic number, that will tell you how many neutrons are present. All right, let's have a look at this. Here we've got carbon. Okay, so the mass number of carbon is 12. The atomic number of carbon is 6. If we take away the atomic number from the mass number, so 12, take away 6, leaves us with 6. And carbon has 6 protons, 6 neutrons, and 6 electrons. Now, having a look here. Okay, so we've got our atomic symbol. Now, this is what we see on our periodic table, all of our letters. Okay, and we've also got our mass number and our atomic number. Now, what you need to be aware of is whatever periodic table you're looking at may have mass number and atomic number in different places. It may have other values on there. So you really need to keep an eye on what you're looking at and choose some base elements that you know to be able to figure out what kind of periodic table you're looking at. But we'll get to the periodic table in a moment. Got a couple more atoms here for you to look at. We've got hydrogen. Okay, it's got an atomic number of 1 because it's only got 1 proton. Okay, hydrogen is quite unique there, no neutrons. You'll see it's got a mass number of 1 because it's only got 1 subatomic particle in its nucleus. It's only got that proton, and it only has 1 electron. The number of electrons and the number of protons are always the same. Okay, here we've got helium in most cases. When you go on to higher levels of chemistry, you'll see that the protons and the electron numbers may differ. When we go have a look at helium, okay, now this is atomic number 2. And as we can see, it has 2 protons. That's why it's atomic number 2. Its mass number is 4 because it's got 4 subatomic particles in the nucleus, 2 protons, 2 electrons. 2 protons, 2 neutrons. And then, because it's got 2 protons, it has 2 electrons. Here we've got carbon, a carbon atom. Okay, so we can see that we've got 6 protons in there. We can't actually see it because this is a really terrible diagram that I've chosen, but there are 6 protons in there. There are 6 neutrons in there. It's just I've tried to draw it 3D and it's really wrecked our picture, but don't worry about that. Trust me, 6 protons, 6 neutrons, and then we've got 6 electrons. Chemical symbol for carbon is C. Now the chemical symbols can decide on various things. The actual name, where the name was discovered and developed. So sometimes the name on the periodic table, for example, iron is Fe. Iron doesn't start with Fe, but it's for ferrous. Okay, and it can also, the symbol can also be related to the person that found the element. It just depends. Okay, so we've got our mass number, 12. Okay, remembering that's how many particles are in the nucleus, and it's a non-atomic number is the number of protons or electrons. Okay, so remembering I said that the number of protons is the same as the number of electrons, and remembering that that's because they've got a positive and a negative charge. Okay, so they need to be the same number for our atom to be neutral. If you have less protons, then you've got an imbalance because you've got more electrons. Yeah, it would not be balanced, therefore it would have a charge. But if the protons and the electrons are balanced, then our atom is neutral. Okay, our atomic theory, carrying on a bit more. Each element has its own atomic number. That's how they're all unique, okay? That's how every element is different, because it has a different atomic number, which means it's got a different number of particles in its nucleus. All elements of the same name will always have the same number of protons. So for example, you have different types of carbons, but they will always have the same number of protons. So for example, oxygen will always have 8 protons, and its atomic number will always be 8. Here's oxygen. Okay, so its atomic number is 8. It's got 1, 2, 3, 4, 5, 6, 7, 8 electrons. If it's got 8 electrons, that means it's got 8 protons in its nucleus. Okay, so we've started to see some diagrams with our electrons in what we call these shells, so these orbital rings around the nucleus, and we call these electron shells. Now, electron shells are different, what we call different energy levels, okay, and within the atom, because they hold different numbers of electrons, kind of like a bookshelf that gets full, and then you put more books in the next shelf. The closer to the nucleus, the lower the energy of the electrons, and the more tightly the electron is held to the proton. So the closer to the nucleus, the stronger the bond. That electrostatic force is stronger the closer you are to the nucleus, because you're closer to the charge. Electrons in the outermost shell have the highest energy and are only loosely held. So the further you are from the charge of the nucleus, the less that electrostatic charge is there. So there's less charge out here than there would be in here. Now, you've got to remember, we're going to be looking at some atoms with quite a lot of electron shells. So the further away from the nucleus the shell is, the more electrons it can hold. We're going to have a look into that in a minute. The maximum number of electrons a shell can hold is determined by the maximum number of electrons. Okay, now we've got this special formula, and we're just going to do a slight recap on how we use indices in maths so that we can apply what we know from maths to our science. Now, N is the shell number. Okay, so a little bit of maths revision now. Okay, so we've got to think of our bod mass. You may call it bid mass, bed mass, ped mass, pod mass, a range of things. It doesn't matter what you call it as long as you know what it represents. And that's this order of operations. Now, if we look back here, we have an index that we need to use. So we've got 2n to the power of 2. So that means 2 times n to the power of 2. So we need to do this index before we can solve this whole problem. So, sorry, pass the orangutan again. Okay, so let's have a think about this. If we've got an index, what does that mean? So if we've got 5 to the power of 2, that means you've got to multiply 5 by 5. It means multiply the base number by the amount of times the index says. So 5 to the power of 2 is 5 times 5. If it was 5 to the power of 3, it would be 5 times 5 times 5. Okay, what did that have to do with electron shells? Well, we've said that to find the maximum number of electrons in the outer shells, we've got to, or that the shells can hold, we've got to use this formula. N is the shell number. Okay, so here we've got shell 1, shell 2, shell 3, shell 4. We need to use this formula to find out how many electrons that those shells would hold. So for shell 1, we'd have 2 times 1 to the power of 2. Okay, so 1 to the power of 2 we need to work out first. So 1 to the power of 2 is 1 times 1, which is 1. So then we've got 2 multiplied by 1 is 2. All right, if we have n is 2, we've got to do 2 to the power of 2. So that's 2 times 2. So 2 times 2 is 4. And then we're going 2 multiplied by 4 is 8. Okay, we've got n is 3, so we've got 2 multiplied by 3 to the power of 2. So 3 to the power of 2, 3 times 3 is 9, and then we're going to go 2 times 9 is 18. Okay, so now we've got n equals 4. So we've got 2 times 4 to the power of 2. Okay, so 4 to the power of 2 is 4 times 4, which is 16. And then we're going to go 16, 2 multiplied by 16 is 32. So that's how we work out the maximum number of electrons, okay, that the atom holds. So the maximum number of electrons in those shells. Okay, so electron configuration can either be written or it can be drawn. So it can be written as a list of number of electrons from each shell, starting from shell 1. Okay, and we use a comma between them. So let's have a look. For example, we've got carbon here. Now you can see with carbon, it's got 2 electrons on the inner shell, so that's the 2. So we're going from left to right here. And then we've got 4 electrons in the next shell. So we put a comma for 2 in the first shell, 4 in the next shell. And that makes 6. And carbon just happens to be element number 6. Okay, so if we look at argon, argon has an atomic number of 18. This means it's got 18 electrons. Shell 1 can only hold 2 electrons, remember. Shell 2 can only hold 8 electrons, or has 8 electrons, can have 10 all up. Shell 3 has 8 electrons. It can have 18 all up, but it depends on the atom how the electrons are arranged. So argon has 2 in the central shell, then 8, then 8. Okay, here we've got argon. Let's have a look. 2 in the first shell. 1, 2, 3, 4, 5, 6, 7, 8 in the second shell. 1, 2, 3, 4, 5, 6, 7, 8 in the third shell. Written as 2, 8, 8. Alrighty, let's do some quick revision of the periodic table. Here it is, the periodic table. Every element known to man is recorded on the periodic table, and the periodic table has grown much since I was at school because new elements are discovered. Will you find water on the periodic table, H2O? No, because water is a compound. You'll find hydrogen on the periodic table, element number 1. You'll find oxygen on the periodic table, element number 2. So the 2 elements that make up water are on there, but not water because it's a compound. Okay, so our periodic table is a list of all the known elements in order of their increasing atomic number. It's arranged in rows or periods, so rows go across 7 rows in total, or 7 periods, and 18 columns, so columns going down. These are what we call groups. The arrangement gives information about the electronic configuration of the elements. So it's arranged in this way for a reason. So let's have a further look. Now, remembering electronic configuration is the arrangement of the electrons in each element. Okay, so we've got to remember that because it's the arrangement of these electrons that decides which location in the periodic table an element falls. All right, so those rows, the horizontal periods, they're labelled 1 to 7. They indicate how many shells are being filled with electrons. Groups, vertical, they're labelled 1 to 18, and they contain elements with the same valence shell electron number. Whoa, what's a valence shell? Well, a valence shell is that outer shell. Okay, and what this is talking about is what number shell the valence shell is. Okay, let's have a look at that further. All right, so here we've got a small snippet of the periodic table, and you can see that all the columns, okay, have 1 electron in their valence shell, so in that outer shell. If we go across, we can see, so if we're looking at the rows or the periods, we can see that they all have the same number of shells. So for example, looking across here, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon all have 1 shell. Sorry, they all have 2 shells. Okay, hydrogen and helium only have 1 shell. These guys across here all have 2 shells. These guys across here all have 3 shells. Okay, so looking at what these have in common, they all have 1 electron in their outer shell, so that valence shell. These all have 2 electrons in their outer shell. These all have 3 electrons in their outer shell. These all have 4 electrons in their outer shell. Okay, so it's telling you number of shells and number of protons. So on this periodic table, I've put this one on because it's showing a few different groups. Okay, here we have our metals. Here we have what we call our metalloids. Okay, so it's the same periodic table. Whatever you see, it's always the same periodic table, but they show different things. They may have different shadings. Okay, so these are our metalloids. They're kind of stuck between the non-metal and the metals. Okay, they're not quite metals, they're not quite non-metals. And here we have our non-metals with hydrogen over here. Okay, so metals, metalloids, and non-metals. Okay, we've got different features of each of these. Our metals tend to be shiny. They're generally solid at room temperature, except for our mercury. They're good conductors of heat and electricity. They can be bent or hammered into sheets, and they can be stretched into wires. We call that malleable for being hammered into sheets and ductile for being able to be stretched. And now non-metals, they tend to be dull. They don't conduct heat or electricity. They break or crumble when you bend them. And then our metalloids, those things that kind of stuck between the two, they're a mixture of the characteristics and the features of our metals and our non-metals. So, the blocks in our periodic tables, we've got our main groups of elements on the two outer wings. We've got our transition elements there in the middle, our lanthanides and our actinides at the bottom. We'll talk more about them as we move along. Again, just in representing those metals, non-metals and our metalloids. This is just showing those features of the periodic table here. Okay, a very, very quick, I promise you, 2-second introduction to bonding, because that's what we move on to next. Okay, so bonds are made from the transfer, the loss or gain, or even the sharing of those electrons in that outer shell. So this is how bonding is going to link to what we've just done. All bonding is electrostatic. It's an attraction between the positive charge and the negative charges. The type of bonding between atoms in a substance determines the property of that material. We've got 3 types of bond: metallic, which is metals and metals bonding; covalent, which is non-metals and non-metals bonding; or ionic, which is a non-metal bonding with a metal. We'll see our next video for more information on bonding. It's just a little cartoon. See you in the next video. Thanks for watching.